Yeah, all good.
Okay, we're talking about sound wave, and I got these 4 objectives that would like to talk about. And we're going to interact. We're going to interact. So don't mute yourself.
Yes.
We're going to talk. If you do not understand something, you can interrupt and you can ask me. And as much as possible, try to minimize the noise from the background. So we have a, we do not have any unnecessary sound. It might distract the session. So these are the 4 objectives or the outcomes that I have for us for this session. We're going to define sound wave and identify characteristics of sound. And the third one is investigate the processes through which sound travel, and finally identify the behavior of travel of sound waves. So basically, it sounds like 4 big areas, but we'll try to make it short and simple within this 30 minutes. So let's proceed with our presentation. So sound wave is what we're looking at. So question is, what is sound? Well, as you can see, sound is an invisible form of energy. Sound is not just a wave, but it is a form of energy. And so it can be damaging at times too. I got a video. When you come back, I will show you that video, how powerful sound could be as a form of energy. So it is, in fact, sound wave is, in fact, an invisible form of energy. And sound is produced when energy changes from one. When energy changes from one form into another, sound is produced. So sound is produced when object receive enough energy to vibrate. Example, like a string of a guitar. When a guitar string is when you are strumming a guitar, what you're doing is you're basically using movement, which is basically kinetic energy. You're using kinetic energy to change that. When kinetic energy is converted, it produces the sound. And much more detailed discussions should be done in class when you come back, obviously or hopefully next week. And that's that. And also from what I have here is a drum, kundu drum. When a drum is, when someone is hitting the drum with some force, kinetic energy is converted into sound energy. So basically changing from one form of energy into another. So sound is in fact an invisible, we cannot see, but it can be converted, or it's basically the conversion of other forms of energy like kinetic. Sound are produced by vibrating objects known as a source. So when sound is produced, it has to come from some source, which is known as the source of sound. Say, for example, like a string is a source. Like I'm talking right now, the sound that you hear, I am actually the source, and you as on the receiving end, but sound needs to travel through a medium to really fulfill the concept of in communication. We have three components that give us the complete understanding of communication. What is the first one? Anybody can remember? There has to be a sender. There has to be a receiver, and there has to be a transmitter. So sound is produced from some source, transmission is done from some source, and then it is transmitted through a medium, and there is a receiver on the other end. Just like what's happening right now, I am actually talking, the transmission tower, radio wave, it is becoming the medium through which we can communicate, and you as a receiver on the other end. So that's basically, so sound is produced from some source, and it is transmitted through some medium, which actually give us the complete understanding of communication. Now, I hope this is straightforward. Let's move down to the characteristics of sound. Now, characteristics of sound, sound is actually associated with certain characteristics. The first one is the pitch. The second one is frequency, and pitch, they are closely related to each other. And pitch, what is
proportional?
It basically gives us the how he is actually tell if the sound is louder or not. Pitch actually gives us that sense. So pitch describes how high or low sound seem to our ears. And that's what pitch is. Now, frequency, on the other hand, we also noticed, we discussed frequency some time ago in previous sessions. And we said frequency is number of complete cycles produced in 1 second. But because we are talking about sound, sound is basically produced by vibrations. What happens is that frequency, there's a number of vibrations that are done in just 1 second.
Take that shit out the screen, man.
Who is that?
Yes.
Bias. Bias.
Bias.
All right. So this frequency and the pitch. When you take a look at the third point here, low pitch sound as low frequency, while high pitch sound as high frequency. What does that mean? It means that they are
proportional to each other.
Yeah, yes, exactly. So they are in direct proportion to each other. And so the higher the frequency, and the lower the pitch, the lower the frequency. So again, they are in direct proportion to each other. Well, when sound is produced, I'm moving on. When sound is produced, it needs to travel through. Say, for example, like I am producing the sound, it needs to travel through a distance to the receiver's end. So how sound travels? Well,
It's vibration.
Air is basically a medium through which sound is traveling. So sound can only travel through air. If there is no air particle, sound cannot travel. That is no medium to which sound could travel. Sound cannot travel through vacuum. Why sound cannot travel through vacuum? Anybody?
No air particles.
Because they're low.
Very good. Because there are no air particles, sound cannot travel. Sound travel. I would like you to take a look at the second point here. I got the second point. Sound travels fastest in solid and slowest in air or gas. And I got this particle arrangement of solid, liquid, and gas. Do you understand why I have to say sound travels faster in solid and the slowest in half. I am going to use this particular arrangement to explain that, but anybody got any idea why we have to, anybody disagree with this idea of solid in the medium to transfer sound energy faster than liquid? Yes.
Because everything is compact, so sound travels faster in solid.
The distance is shorter.
No.
No, mister, everything is compact. The particles are compact. That's why it travels faster.
That's right. That's right. So when you take a look at the particle arrangement, the solid particles here, the distance from one particle to the next, it's short. So what happens is that when the air particle receives the, pardon, not the air particle, when one particle receives the sound energy, it does not, it travels a very short distance to pass on this energy, sound energy, to the next, and to the next, and so on. So you could remember those relay. Have you ever tried those relay, button relay? Have you tried that game before? You had to carry the,
Yes.
all right. So what happens is that the shorter the distance, the faster you can pass on
Athletic.
the button. Yeah.
Yeah, mister.
So the longer the distance, it needs to, whoever that is carrying that button to pass it to the next, it needs to take some time, covering more distance and so on. So that's exactly the same thing that we can see in this perspective. I mean, the whole concept here, we can see it from that perspective. The shorter the distance, the faster it travels. And gas, the longer the distance, the more time it takes. So there is a delay somewhere there. That is the whole reason. So sound travels faster in solid, followed by
Liquid.
Liquid
gas is
and gas.
And gas.
That's right. Gas is the one that travels the slowest.
Lowest.
That's right. So how sound travels? So sound definitely needs a medium to travel. A medium, it could be either solid, liquid, or gas.
Yes.
And once it
Or gas.
goes through each one of those mediums, what happens is
What?
solid is the fastest, gas is the least. I hope this is clear.
Liquid.
Yes, madam.
This fastest. Yes.
Now, how sound wave moves forward and backward with, which is an example of a wave. Do you remember those two types of waves?
Maybe.
Which one?
Transverse.
I'm talking about the first point here. Sound wave moves forward and backward, which is an example of a longitudinal wave. What is the other wave?
Latitudinal.
Transverse wave.
Not longitudinal waves.
Transwave.
Transverse waves. Transverse
Transverse wave.
waves. Okay. So it's right here. It's right here.
Yeah, there.
Yeah, that's it. Unlike water waves, moving up and down. So sound waves, they are moving forward and backward. In other words, sound wave, they are the particles. When they receive the energy, particles move in parallel with the direction of the motion. Sound wave is an example of a longitudinal wave. Longitudinal wave particles are moving parallel, whereas transverse waves particles are moving up and down. What does that mean? Perpendicular.
Perpendicular.
Perpendicular. Forward and backward, it means parallel. Right. Now, in longitudinal waves, the wave particles, they are described using these two terms, rarefaction and compression. Those are two terms that are used. And rarefaction is stretches of air particles, and compression is squeezes or clustering when air particles are actually coming together. Let's take a look at this diagram here. It actually
Portions of air particles.
is the kind of a diagram that you will see when you're talking about the longitudinal waves. Transverse waves happens like this. Do you remember something like that? A kind of a wave pattern. Do you remember something like that?
Yes.
Yes, Mr.
Okay, the wave on the screen here, this is an example of a transverse wave. But what we see from this one here, this is an example of a longitudinal wave. So you can tell the difference between a longitudinal wave and a transverse wave in terms of representing them in sketch like this. What we have is a longitudinal wave. Transverse waves like that. That's the difference. Okay with you?
Yes, Mr.
Good. That is the difference. So how can we describe this transverse wave? Well, when compression, we talk about compression, that's when you see those wave fronts. They are called wave fronts, but when they are clustering together somewhere here, when they are, when they...
How do you spell it?
What is it?
How do you spell it?
Come again?
The word you just said. How do you spell the word you just said?
Compression. Compression is
No.
when the fronts, when the wave fronts are actually
I'm so talking about that.
clustered together here, when they are... Yes? That is the time when they are described using the word compression. And rarefaction is when they are scattered apart. It's more like when you come back, you're going to use a slinky spring to demonstrate that. I also got a picture. I'll show you. So when the wave fronts, when they are close to each other, they are further away from each other, it's called rarefaction. That is the, those are the two terms that you're going to come across in longitudinal term, longitudinal wave, and these are the two terms that are used to describe this wave pattern. Is that okay?
Okay.
All right.
So can you put the presentation
Yes,
on
Mr.
the one so you can download it?
Okay.
Yeah.
Okay. So that's actually from a spring. When they stretch out somewhere here, it's described as rarefaction, and when they
Rarefaction.
so that's basically that about the idea on sound wave. Who's that?
Yes.
Oh, yeah.
Yes. Who's breaking bone?
Yes, it's
Okay.
It's not me.
Why is this some yoga?
No problem.
All right. Now you got the speed of sound in echo. The sound travels from one point. As sound actually travels in those different medium, be solid, liquid, or gas, it needs to travel with some velocity, some speed. So when it travels with some velocities, we need to calculate that speed. And the standard speed or the standard velocity to which sound travels in air is 330 meters per second. Make note of this value. Can anyone remember the speed of sound in speed of light in air?
3 miles
Yeah.
per second. 300
3
miles.
miles.
300,000.
Per second.
300,000 miles per
300,000
second.
300,000 kilometers in 1 second. So this is the
Yeah.
speed of sound in air. So sound travels at different speed in different medium, and like we said in those in the previous slide, because of the particular arrangement, sound travels faster in solid, followed by liquid, and gas is the one, or air is the one that sound travels. That's a lowest possible speed. Now let's move a little bit further down, and these are the different. Basically, this is an extraction from your textbook. So you can check this out from your textbook. So as you can see, glass being solid, 5,200 meters per second. Water, liquid, 1,210 meters in 1 second, and 330 meters. That's air. So those are examples of speed of sound from those three different mediums. This is also an extraction from your textbook. So as you can see from this, there's one important thing that I would like you to make note about this particular example is that the time taken for a sound to travel. Echo can be used to work out the speed of sound as given. Figure 5.34 is from your textbook. The boy is standing 330 meters from a wall. He fires a static pistol. His friend is the echo 2 seconds later, which means that the friend is somewhere here, and the person who is actually firing the pistol is somewhere on this end. He fires the pistol, sound travels in one direction, it bounces back, and the friend actually hears that. Time taken is 2 seconds, and the distance covered is 330 meters. So 330 meters is the distance. Sound travels from this end to that end and back again. It takes 2 seconds, which means that if time taken for the echo to be heard is 2 seconds, that means that the sound travels twice the distance. The distance from here to there is 330 meters. Then from there back again another 330. So that's why you see that distance traveled is 2 times 330, and the time taken is 2 seconds. The formula speed is equal to the distance given over time taken. The speed of sound in air is given to be 330 meters in 1 second.
Really?
So that's basically that. Again, importantly, sound travels faster in solid, followed by liquid, and air is the one that sound travels the least. The reason, because of their particle arrangement. The solid particles are tightly compact together, therefore sound energy, the particle needs to travel a short distance to pass on the sound energy to the next particle, and sound travels from one point to the other. It travels a very short distance to deliver the sound energy. Whereas air particles are further away from each other, so it needs to travel a distance. That is the whole reason. I think that's all for